Alright, we're on the air. Good afternoon, or whatever time it is in your place. My name is Bernardus, and today we'll be closing C programming 2 months. Yes, 2 months of C programming finally coming to an end. Let's open. Let's open my roadmap, right? Yes, 6 issues. This one will be closed today, one day late. I should have finished this yesterday, but yesterday I was too lazy to even bother do it. Alright, so let's get this finished today. Alright, header, extern, warning, and sanitation. Shalom. Yes. Alright, let's get the walk hot. We're doing this fast. So before we dive deep into header extern, we need to know how does C compile up, how does your compiler GCC or Clang compile your C source codes into binaries. So we have two compilers in C worlds, as I said, GCC and Clang. But what we are gonna be doing is see the requirements of C compilation, not how they compile, as GCC and Clang have different ways of turning your source code into binaries, but the requirements or the steps in doing so are similar, if I'm not mistaken. So the first step is pre-processing. So in this step, it doesn't care about the entirety of your code, only specific parts. Preprocessor commands and comments. Wow. So anything beginning with ampersand, not ampersand. Got my emails. Alright. You genuinely gotta be kidding me. A number sign. Hashtag, yes. Hashtag. Oh my lord. Alright. Let's forget about that, alright? So anything beginning in hashtag is a preprocessor command, including define, include, if not defined, etc. And for include, this is basically what we're gonna be doing today. It basically copy paste your imported header files, .h files. You can prove this by doing this command right here. We'll do this, alright. Oh, this is all my main pages I used to create the CLI. Good God. Alright, let's paste this one. It'll generate main.txt, and as you can see, this pretty much. Oh my lord, how big is this? Oh! So okay, as I said, in my main.c, I include spy.h, and inside spy.h, I include all of this. So if I'm not mistaken, again, correct me if I'm wrong, this basically copy paste everything into these header files, and then inside these header files get copy pasted on top of my code, if I'm not mistaken. Yes, there are pthread right here, but yes, there's pthread, so that's basically it will be a big blob of definition before your code is even visible. Because if you see right here, my code is only visible on the bottom. See, this is the spy.h, right? Spy.h, and then this finally we get into the main command. Alright. As for command, that's the opposite. It strips away every command. It deletes them. So every command of yours will be deleted by the preprocessor inside the preprocessing part. Yes. Now compilation. Now as its name suggests, this basically turns your preprocessed code into assembly, the last humanly readable version of a specific CPU architecture. Let me try just a bit, alright? If I'm not mistaken, yes, this produced the assembly code right here, the readable version of CPU instruction. And then the last one, assembly. But not the last one. Text.s file takes assembly file and converts it into binaries, resulting in an output or .o file. What a gotcha! It has holes in it. I forgot how to compile it during this. Let me try. All right. Yeah, no. I forgot how to do that, but this basically outputs .o file. So now we have our binaries, but what's the problem? Simple. You included the definition of the function, not what does the function do, not what's inside it. So it has holes in it, as I said, but not the function itself. So your binary file has holes because your printf function has no implementation. So this phase sees your .o is asking for printf, and it will search for it, passing the binary inputs. So now we have pre-processing header. So now we know that everything beginning with a hashtag is a processor command, preprocessor command, or preprocessor directive to be precise. It tells the preprocessor what to do. So these are some of the most common preprocessor directives. The first one is include, as you can see, it's used quite a lot. Yes, quite a lot. Include the content of this file. It doesn't matter if it's header, C, or C++, it's just perform copy paste. However, the difference between less than, more than, and just quotes is that less than and more than looks in the system folder or the C compiler files, while the quotes looks inside your working directory, your folder. Yeah. Again, correct me if I'm wrong, but this is my mental model. So now we have define. Just perform text substitution. If you define pi as 3.14, the preprocessor will literally replace every instance of pi with the number 3.14. So it's just copy paste, replace. Alright. So now if def, this is a part of a header guard. So if you declare something twice, it will have catastrophic consequences if I'm not mistaken. Wanna try it? Wait, let me remove these two. Do I still have that one? Yes, I still have this one. I'm gonna save this one for last. Oh, this is, wait, where? Oh, nah. So now let's go to this. We go to, I'll just probably later. Alright. Let us see if, so to do that, we'll include stdio twice, and oh no, it doesn't throw any error. This is sanitation and warnings. It will be, wait, huh? Oh, sorry. These are warnings and sanitation, which we'll discuss later, but it's quite wait. Oh, if not the point. Alright, I don't know what happened. Once it throws a bunch of text into my terminal, I don't know what happened now, but it's basically a guard to make sure that you doesn't include your definition twice. That's it. Just from text substitution. This is the polar opposite of if defined. If not defined, do this. It prevents redefinition, same as if defined. Basically tells the processor this is the this line is the end of if, and undef basically undefined a macro, which if you define something using define and you want to undefine it, use undef. Pragma. This directive tells the processor to do a special request. Either do a guard check like if def and if not def, which is used in modern guarding, but I'm not really using it today, or something else. Error tells your compiler to stop compiling with an error message. That's basically it. for pre-processing. And then we have extern, basically I promise you later. So extern basically means I promise you this exists somewhere else. I'll use it now though. That's it. When you import a global variable through header file, it will later be combined in the linking stage of compilation. The danger, you cannot check safety at all, whether you already declared it or forgot to add the word extern. As you can see, I declare it in another file called second.c, and this is main.c. I can print it pretty well. You need to compile both, and the linker will combine them accordingly. Because during the linking stage, they will be combined into a single executable, a.out. That's quite... How did I talk for 10 minutes already? I yapped too much. Alright, so let's get to day 2 real fast. Shalom. Alright. The first one is warnings. As its name says, it's warning. It warns you of unpredicted behavior, which is... Excuse me for a bit. Now I know why it already... Yes, undefined behavior. In your source code before you compile rather. Yes. It may say warning all and with extra warning extra, but it doesn't catch every instance of undefined behavior. Only the most important one, like reading an initialized variable and quote-unquote valid human error, like initializing a variable inside a nav, etc. Remember the saying, for warning error, remember the saying. If it compiled, it won't be guaranteed to work. This flag is passed to make sure that every warning will throw an error, so it won't compile. Yes. So now we get into sanitizers. So sanitizers basically injects a watcher into your code to make sure your code is quote-unquote safe. It won't be 100% safe, but will catch most bugs you'll encounter. With the first one, we have sanitizers address with the nickname as_sun address sanitizers. If your program ever does anything violating the memory, the watcher will immediately crash your code instead of doing UB and tell you which line messed up. And then we have UBSUN, undefined behavior sanitizer. Now it does what is named UB. What it does is basically, if your program ever does this spooky stuff in C standard that might work on your machine but explode on a server, like dividing by 0 or integer overflows, it'll print a warning to the terminal and keep the program running. But if you want it to terminate your program immediately, strip fno strip sanitize strip recover equals undefined. However, as its name suggests, it injects something. Sanitizers inject a watcher into your code, adding RAM and CPU overhead, so only use them for development. And use optimization flag once you know your code is safe, like O3 for the fastest performance. That's it. Quite short, huh? So now, for the rest of my time here, I will talk about the CLI that I created. I have opened it right here. Yes, you can see it under github.com/bernardus /proc_stuff. So let's get into the VS Code already. Open the readme.file. So procstat is a CLI utility written in C that monitors process statistic for one or more specified process IDs or PIDs. It leverages multi-threading. I know what you're thinking. I used AI to generate this readme. I'm gonna be clean, alright? I'm quite lazy already. Yesterday I slacked a lot, and today I needed to finish this real quick. But I understand every single line. I used AI, but I don't let it write every single line of my code. I reviewed, I refactored everything. So let's get back. It leverages multi-threading to efficiently collect data in parallel. Not 100% efficient, but because I have sequential parallelism, which basically means I'm collecting state and memory, right? So before collecting memory, it needs to collect the state first. After all threads are finished, only then we can collect memory. So it's sequential parallelism. It's not 100% efficient, but cut me some slack, man. I haven't played any game this week. Okay, providing information on process state, either running, sleeping, and memory usage, resident set size. I don't know. It's basically just show how many memory does this process use, along with its percentage relative to total system memory. The features, it shows process state, as system suggests, memory usage, physical RAM usage for each process in kilobytes. Then we have memory percentage, multi-threaded data collection, uses POSIX threads or P threads. Oh, okay. Robust error handling. I don't know if it is truly robust, but that's okay. Main.c. This is the entry point of the program. Process command line. Basically, this is the orchestrator, the aggregator. Orchestrator may be the right word, that calls the function saved in processes.c, memory.c, and implemented in spy.h. This is how to compile. This is just a bit of a nice thing to read. Let's get started immediately. Inside main.c, we include spy.h. This is the header guard I said earlier. If spy.h is not defined, we define it. So we include all the libraries we'll use here. This is not efficient once again, but again, I'm lazy. So this is what I do. So basically, I don't know if it is efficient or not. Correct me if I'm wrong, but my instinct tell me that this isn't. So this basically includes all the headers we need. Remember the less than more than. So this is located in the system file. Then I use define, preprocessor define, to say that the buffer size is 120,024, and this is actually unneeded if I'm not mistaken. But again, lazy, so I'm gonna let it be. So we define the data will pass. We have process ID, we have the state in which the process is doing, and then we have the memory usage of that PID, then we have the total memory of that PID, and then we have the memory percentage. The struct is called process data, and then we will define the function inside the header file, get process state and get process memory. So that's it. Inside the main function, we check first whether the argument inputted is less than 2. Because if it is less than 2, that means the user didn't pass any process ID, which is invalid. So we'll immediately return 1 for error. And then we create an array using the amount of argument passed. Remember, the first argv argument, I don't know what's the abbreviation of argv for. Let's call it argv, right? The argv arguments, the first one is always the name of the executable of the file. So we'll -1 for all the processes ID inputted. So we create an array, and then for each, this is a process, this is a struct process data, right? Process data struct, and then this creates an array of process data. So for each process data inside processes data array, we assign a process ID. So now, what does this do? This is what I mean by sequential parallelism. I can create another process for this, but again, I am lazy and it's inefficient if I'm... Alright, so the first one, we have get memory state, which takes the entirety of the array, but remember, array decaying, so this is the pointer to the first element in the array. So then we pass in the size of the array. So then we all get into this. This is just the aggregator for all the threads. We get the number of PID, which basically means how many PID we need to check. Wait. Oh yes. Data. Wait, did I do it wrong? Alright, wait. E. Oh, sorry. My past self was correct. My current self is not. Alright, so how do we get the number of elements inside the array? Remember, we pass the full size of the array, and then we have the size of a struct. So we kind of divide it. Yes, divide. So then we get the number we need to go. Then we create a thread for each one of the PID, and then we create it, we initialize it here, and then we make the main thread wait for each for all the children to finish. Why no lock? Because each thread takes control of different element inside the array. So we need no lock because they are changing different elements. Yes. So then we create a worker. This is the thread. We pass in the thread. We pass in the flag, and then this is the function, and this is the input. So we immediately pass in the data they need to work on. This is the first element, and then the second element of the array, the third element of the array. Remember, pointer arithmetic. Yes. Inside the process worker, as usual, POSIX thread, it returns void pointer and takes void pointer. How should I say it? We typecast the argument back into the appropriate type, and then we create a local data. Remember, non-blocking threads. So we create the buffer size. We create the, how should I say it? A string to hold the path, since we need to like have a dynamic PID, and then we open a file descriptor. Yes, wait, alright. Going to open. Opens the file. Yes, we open the file descriptor to that path which is inside the proc. If I'm not mistaken again, alright, proc is basically a Unix way of seeing live processes, if I'm not mistaken. Correct me if I'm wrong again, alright? So then we open it, then we check, did we successfully open the file? Because if not, we print error opening the stat file, and then we immediately set the state to unknown. And then we create char buffer again, and then we read to the buffer from the file descriptor. We read what's the current state, and then we check, is the size of buffer not empty? Because if it is empty, unknown immediately. But if it is known and we get something, we immediately convert it to a string using string terminator, because read doesn't immediately input the string terminator. I don't know if this is called null terminator or string terminator, but I'm gonna call it string terminator. And then we create a string which is a char pointer. We create a pointer to the element starting with the closing what again? I don't know. Penutup kurung. Bahasa Indonesia penutup kurung. Aku nggak tahu bahasa Inggrisnya. I don't know the English one for this one, but basically the closing of, yeah, you already know. And then we advance by, and then we make sure to check, does this actually exist? And if it exists, and if it does exist, we go by 1 and check, is it a space? Because if yes, we go again, one step again to the front. So like this. this is the closing, this is the space, this is the closing, this is the space, and this is the start of the, and this is the state. The state is only a char. So we check, does this exist? Because if this exists, we go up by 1 and check if this is a space, then we go check up, and then we take this last one. That's basically it. And then we close the file descriptor, so no leaking, and then we need no log, remember? We need no log. So we immediately convert the current data passed to the equals to the local data. Good. That's basically it. And then we go back to main, and then this is what I call sequential parallelism, right? Because it needs to make sure that this line is finished first before going down to the next threading, which is not really efficient. It's pretty much the same as the process state, but the only difference is this one takes this is the aggregator again, once again. But the difference inside of this one is that it takes out what each thread don't need to do, which is take the total system memory, since it'll be the same. Your RAM doesn't change, alright? Your RAM doesn't change in the middle of a program. So it checks the RAM, and then call this function, which returns the amount of total memory in your system. It creates a buffer size, and then it reads from the RAM data. It reads from the file descriptor passed down, which is, if I'm not mistaken, yes, the file descriptor to memory info, and then afterwards, where is it again? Yes, total system RAM. Remember, we need to make sure it is read as string, so we add the string terminator, and then we use str to search where does this exist, and if it does exist, it returns to the pointer to that char. And then if the result pointer isn't null, we use scanf, read formatted input from the mem total and passed it to the address of total memory to here, and then we return it because it returns a long integer. So that's basically it. Total system memory, and then for each, we close it, right? We close the RAM FD, and then for each thread we assign the total memory so they don't crash on each other. So then this is for each thread, this is the same. We create a thread, and then we enter the memory worker. Inside each memory worker, we convert it back. We create a stack data, a local data, and then we create a buffer. We create the path. We construct the path, and then we open the file to the path, and then check, does this succeed or not? Because if not, yes, sets to 0 and then escape. But if it does succeed, we set the local data to the appropriate data, which is get process RAM. We have a buffer again right here, total memory. We read it, and then we add string terminator again, and then scanf, this asterisk tells the syscalls to skip the first integer, because if I'm not mistaken, the mem info stacks like virtual memory and then the real physical address. So skips the first one and then get the second one and pass it to the total memory usage, this long integer right here. But this is the amount of page, if I'm not mistaken. So we need to get the page size in kilobyte, get the value. I don't really know what does this line do, but this basically converts it. But this basically get the size of a page, usually 4 kilobytes, and then we return it to each worker. Memory worker, yes, we return it right here, and then we close the file descriptor. That's for searching how many RAM usage a process do. But then we need to take how many percentages that each processes use. So we use this one. We use typecasting for double, so it will floating arithmetic if I'm not mistaken. But if the total memory is 0, we just put it 0 0, and then we put it into the global data and done. Boom, void finished. Main.c is already finished. We already reached this line, and in this printf, I didn't make this. Alright, this table looks pretty nice, but I didn't make it. Where is it? Yes, this one. So this basically creates a table like this, creates a table like this, and then below it creates a table like this with the inputted format: PID1, the state, the memory usage, the usage percentage, and then it prints the total amount of memory inside. Because the total memory are all the same, we can access the first index and then boom. Oh, ngajar. Boom. That's it. That's it. We succeeded in receiving, if I'm not mistaken, one is the system D or whatever it is, and then for now the 4200 is the process ID for these main pages right here, and then we have 4638, it's these main pages right here, and then we have 6447 is for these main pages right here, and then yes, another one for these main pages right here. I literally opened this many main pages in order to build this one. Wait, what did I change? Oh, right. Boom, finished. And with that, let's end the C series right here. And with that, our C adventure has finally come to an end. Yes, we've gone from learning undefined behavior to pointers to memory to process and threads to system calls, and finally this week we learned this one. Yes, I'm gonna paste this entire obsidian right here. Yes, this is basically what I do every day. Not every day, but yeah. Now I'll edit this one. I'll probably upload it raw to YouTube because I'm lazy. And yes, jumping like that takes 30 minutes apparently. So yeah, that's pretty much an achievement for me. I finished C, and then next week we'll dive deep into Java. Yes. It's not the modern languages, but if you do see inside my engineering roadmap, I have this roadmap right here. We finish C, system thinking era, and then we'll go into structured thinking. For 2 months, we'll be diving deep into Java. I thank you pretty much for... Does anyone ever watch my video? Alright, whatever. If you watch it until the end, I thank you very much. This is a documentation learning. Feel free to correct me if I'm wrong. And I, Bernardus, signing out. Thank you.